It's my great pleasure. It's my great pleasure to introduce Loukas Paraschis. He was a student in applied physics, working in my group in the 90s. And he did some very important work on material science and optical recording. We were, in some extent, also involved in optical networking, and particularly optical interconnects and backplanes. And so it's incredibly gratifying to see that 20 or so plus years later, he's making a lot of progress, making this a practical problem that can be solved with optics. And so he's been working in Infinera, and he's also had a very distinguished time period at Cisco. And so it is a great pleasure, Loukas, to see you here. And from time to time, give us an update every 20 years or so. That'd be interesting to see what happens after that. He's also an international traveler, where half his family or more lives in Europe, and he kind of pendles back and forth. And so I know what that feeling is like. So the floor is yours. We're going to record the presentation so that the student can get access to it. And you've given kindly your permission to do that. And so please, proceed. Oh, by the way, maybe for anyone who wants to make comments, and you can do that during the talk, Loukas said, so feel free to ask questions as you desire. Loukas.
Thank you. Thank you very much, Bert, for the kind introduction and, of course, for the invitation. Yes, as you said, I would prefer to make this as interactive as it's possible given the Zoom. I wish we had the opportunity to be all of us together in the room in actually personally at the Kingston lab, but now the new AP building. But that aside, as I was preparing, I was reflecting on my Stanford days, and clearly Stanford has been one of the most important, insightful periods of my life in many ways. And specifically, as I was saying before, AP 483 seminar has been very insightful in many ways in my career choices. I remember back in 94, late 94, early 95, when Bert gave a seminar on a project that he was starting using some work he has done on photorefractive materials to build an optical digital information system using optical multiplexing to store information, what most of us are subsequently known as holographic digital data storage systems. And I was one of the people that joined his group and worked on that, and it was a phenomenal experience in many ways because it allowed me to better appreciate not only applied physics and optical devices and material physics, but also appreciate the aspects on the system level, electrical engineering, if you wish, aspects, and try to bring them together. I also remember David Miller, when he was joining Stanford 2-3 years after Bert's talk, started talking about the challenges in scaling optical interconnects, and actually the challenge of scaling electrical interconnects and how optical interconnects can help that. And in some respects, what I'm going to talk today draws to that, these observations. I also remember after I graduated, I keep following some of the seminars at AP 483, and I learned a lot. And one of them, I remember a researcher from Bell Labs, 2005, 2006, gave a very interesting for me presentation, start exploring what were his initial attempt to calculate the Shannon limit in optical fiber systems. And eventually that became an important part of what I've been doing as well. So many insights. One insight that I have not had the chance to appreciate until preparing for this seminar is this is a pretty tough job, especially for someone like me coming from the industry, because one has to really satisfy three pretty distinct audience: the students, the faculty, world-class researchers, and quite often in these seminars, some people from the industry that want to come, learn, and ideally learn the latest and greatest, including some of the most sophisticated details of the innovation that happen in the industry, which naturally somebody like me may hesitate to present in a public seminar because this is something that can only be presented within closed doors in corporations, let alone that during the pandemic, Zoom and the virtual meetings allow everybody to join from everywhere, myself, I spend most of this winter in Europe, and other people may be all over the world. So how exactly do I synthesize all the different perspectives of this audience to come up with something interesting was an interesting challenge. The observation that I will make here is, trying to synthesize these different perspectives, and by attempting on my side to provide a photonics industry perspective on the data center interconnects, which I will argue and I will try to articulate why I consider the current frontier in optical fiber communications. The fact that I do an industry perspective will mean that I'll start mostly motivate the conversation from the top down, starting from the networks, going to the systems, and then to the devices. I'll focus mostly on the systems because that's where my work for the last 10, 15 years has been at Cisco and now at Infinera. And I will try also to have as much a perspective that will be useful educationally, if you wish, as a tutorial. And in this sense, I thought that made sense to serve this purpose today, to start just a couple of, just 20 years back, as Bert mentioned, and start talking about the days that I was graduating Stanford, and everybody was talking really about the IP networks and the routers and so forth, and that was what motivated me to join at Cisco, the R&D group there, trying to understand how to build better routers. And at the time, everybody, the marketing departments were talking about this transition to a new network architecture that they referred to as IP NGN, for Internet Protocol Next Generation Networks. And I think the observation here, in addition to making a joke about the simplicity sometimes of business requirements and so forth, it allows an interesting perspective in hindsight on what it takes to have a significant network architecture evolution, in the sense that you have to have a new service and therefore a new business model, if you wish, combined with new technologies and new technology innovation. In the case of IP NGN, routers were the big system to be innovated at the time, and they were using silicon and electronics, and the silicon speed was scaling only so fast. Moore's law could do better with ASICs, slightly better, but that was not good enough because IP traffic was doubling every year at least, sometimes more than doubling every year. How do you reconcile that? Plus the fact that routers being a store and forward device had to use storage, and the DRAMs were not coming even close to the scaling of silicon or Moore's law ASICs and so forth. So system tricks have to be employed, and indeed these system tricks were employed and achieved almost 3x every 18 months type of capacity scaling for routers. And note that that's almost double the silicon speed capacity scaling, the silicon speed scaling, which was at the time 1.5x every 18 months. And just let's keep that number as a mental note because it may come back useful as a comparison point later. Now, routers were scaling good enough, and that was great, but the people were connecting routers point to point using dark fiber, basically putting a single optical wave per fiber. And that was not scaling. And I remember at the same time, I got up one day very early in the morning from noise outside my window. That was my graduate student apartment. I was still living there. And I realized Level 3 was making a big deal trying to construct metro fibers outside my window. So I got out, took these photographs, and I started appreciating how expensive it is to construct fiber and why WDM makes such a big deal. And we can spend a lot of time articulating how more than 90% of the cost of constructing a fiber network is in the rights of way, and the remaining 90% of the remaining 10% is about construction, and only the rest goes to device physics people and material science people at Corning and elsewhere that build the fiber and the optical technologies. The important point is exactly because fiber is such an expensive proposition, WDM, wavelength visual multiplexing, came and combined with routers to help internet scale in these 10 years between 10,000 late 90s to 2010. And this is a slide presented at AT&T, by AT&T at OFC, showing how the WDM allowed them to meet the IP capacity growth scaling requirements using 10 gig when I was starting, then 40 gig, and eventually 100 gig WDM. This is on-off keying, amplitude shift keying, and so forth. Now, all this was good and great because eventually WDM came to the rescue, and in some sense, the architecture should have been called more fairly IP plus WDM, next generation networks. And everything worked just fine for about 10 years. And then all these new services came along. Google, Facebook, Amazon, Netflix started dominating the networks, especially between Friday nights and Sunday nights with all the movies. We started watching, streaming, and downloading, and so forth. And that started becoming more than 30. And soon enough, as you can see here on this graph, by 2014, more than 60% of the network traffic cumulatively. And people start talking about the next generation internet architecture, or NGI, and all these marketing terms. And I remember at OFC 2011, they invited me on a workshop that was organized by Deutsche Telekom and AT&T to talk about the fact that the internet architecture has to change to accommodate these massive hyperscalers, and Cisco is using the marketing term massively scalable data centers for what Google and Amazon and eventually Facebook and Microsoft have been building. And the interesting observation there for students mostly is eventually it wasn't about internet changing, but it was rather that a massive global dedicated infrastructure to serve the data center interconnects was built. We can provide many interesting data points to substantiate that argument, but here I have a few. OFC 2017 plenary by Google, or specifically showing the 50x growth of the Google data center traffic between 2008 and 2014. Google actually publicly has been talking about the fact that they have two separate networks, global networks, massive networks. One just to interconnect the data centers on the top. They refer to it as B4, and a separate network that connects to the internet peering points, which they refer to as B2, and it has many more peering points because the B4 is about the data centers, and they only have a few tens, it's the order of tens, some 20, 30 data centers around the world. Now, this growth has continued. Here is a slide reported by Alibaba, a very different source, just to show that this is a consistent across the globe. It doesn't have to do with US only and so forth. That shows the traffic for Alibaba more than doubling every year. Obviously, Alibaba was starting from a lower traffic base, so it was easier to double and so forth. But I think the observation is this has become a really explosive growth, and that motivated a global dedicated infrastructure. And the best proof point of that for an audience like AP483, I think, is the observation that by 2014-15, the majority of the subsea capacity was DCI capacity, was not internet traffic. It was capacity built by the operators of big data center DCI networks that they wanted to connect the data centers together. And that is what is captured here. So in this sense, by the way, these last 12 months have only accelerated that trend, exactly because of the work from home and the sheltering in place. And for those interested to learn more, we are organizing with Steve Jobs from Facebook an interesting symposium at OFC on exactly that topic, where some of these massively scalable data center operators with a massive DCI global network infrastructure are going to provide the perspective, along with some operators from Europe and US and APAC. In this sense, I think it's appropriate to now change the dog and say DCI is the big network that everybody wants to build, and maybe that will motivate a career of some students. Joking aside, I wanted to emphasize here that essentially this is why I argued in my title that DCI networks have become the frontier of optical fiber communications. I will share more further on. As we said in the beginning, feel free to ask questions, make comments as we go along. I thought that to best serve this topic in the remaining half an hour, approximately half an hour, we'll spend some time discussing, hopefully I've motivated enough the DCI optical transport network evolution, so we can spend some time discussing the DCI optical transport systems, what is their current status, spend some time understanding the latest physics innovations or physics motivated innovations at the system level, what are the challenges, and then also spend some time specifically on how cloud, which is a subset of the DCI networks, because DCI doesn't necessarily mean that it's about cloud traffic. It can be traffic like Facebook that's not cloud technically traffic, it's internet content traffic or over-the-top traffic, and how cloud networks have evolved, and that has motivated specifically metro DCI systems and related photonics technology to serve these metro optimized systems. And then I'm summarizing throughout the talk, try to provide some outlook. There are also many detailed references at the end of the talk if anyone is interested for further reading, but here are the main references for this talk, which I thought appropriate to highlight versus the 70 plus reference that I have at the backup of the presentation, because these book chapters essentially allow people that are interested to see the delta between the internet architecture 10 years ago. That's the 2016 book chapter I was invited to write for Optical Fiber Communications, volume 6B, and the DCI networks, optical networks, that was reported in the book chapter I wrote in Optical Fiber Telecommunications book 7 that came out about 15 months ago. The 70 references in that book chapter provide all the details. I'm talking 75 references. I highlighted here 3, I think, very useful references for anyone interested to understand the perspective of the network operators of this massive DCI global infrastructure, to Google plenary talks, and one very, very interesting reference from Amazon claiming why DCI will grow by at least 2 more orders of magnitude in the next few years, given where things are. For those interested also, OFC 2001 has a few presentations and seminars and sessions and workshops on this topic, including these 3 ones I'm directly involved to, so I can definitely, I know enough details to make reference here. Happy to discuss more at the end of the talk. Also, this presentation could not have been possible without many, really too many insightful contributions through interactions with colleagues at Infinera, before that at Cisco. I mentioned some people here that I had the pleasure to interact and have definitely contributed. There are many more. I also want to make clear that this work is multidisciplinary, so no one can see the whole picture. And I learned a lot by talking from people with computer science background, more electrical engineering background, people that have much more knowledge about physics and optics than I do by now, and so forth. But the multidisciplinary aspect is really interesting. I also want to make very clear that my acknowledgement here is not suggesting that any of these individuals bear any responsibilities for any errors I may make. While many of the things I say are thanks to them, and many of the things I say correctly are thanks to them, none of what I say is really incorrectly is really their fault. So let's start with move on to the systems, to the optical systems aspect, and how this makes it interesting and fun for applied physics. And before I proceed, I want to avoid any lingering conclusions by offering some definitions. There are many ways we can discuss DCI use cases. For example, data center interconnects between massively scalable data centers of Google are shown here. Obviously, there are the data center interconnects that used to exist since the 80s between two data centers of a big enterprise, which were running their IT, and sometimes they will have dedicated infrastructure for that. Sometimes they will use telecom infrastructure for that. And obviously, all these data centers connect to the end users through the internet and the telecom networks and so forth. So you can spend a lot of time qualifying the different use cases and subcategories, but because the traffic between data centers of these big internet cloud and content providers dominates, I think it suffices to say this is what we're talking about. And the best summary of that comes from this slide that was presented at OFC 2016, invited by Facebook, that shows that the majority of the DCI traffic is non-internet traffic, is dedicated traffic between data centers. And as a specific proof point to that, I have a reference in my book chapter. Facebook has reported that some 99.9% of their traffic is traffic between the Facebook data centers, and only 1 bit out of 1,000 or 2 bits out of 1,000 go to the end user, just to get in perspective. Therefore, initially, people start building these data center interconnects using the internet network, and therefore using technology in routing and optical that was developed for the internet networks. But soon enough, they realized that doesn't make any sense, and they build a dedicated DCI infrastructure and start requiring optimized technology for that. And that gave essentially the impetus to build, in addition to the dedicated networks for DCI, dedicated systems, transport systems for DCI that were essentially optimized for DCI. And from at system level, that meant let's try to make them as much as possible like servers. So we can stack them then exactly as they do with servers. They're used to doing with servers in data centers, one top of the other, and scale. And that meant let's try to put as much terabits per second per rack unit, which is the unit of measurement for volume in data centers, and let's try to do it as power efficiently as we can. And that gave significant motivation for photonics integration, and I'll come to that. Also, it meant that they have to introduce as much as possible software openness and programmability through application programmable interfaces. And that is a fascinating topic that actually introduces programmability into optical transport for the first time so explosively, leading to open line systems and open transport architectures and all these very important industry initiatives. But given that this is an applied physics seminar, I think it's much more appropriate to focus on the underlying technologies. For routing, it was simplifying routing, trying to maximize the throughput of packets and avoid unnecessary complications in terms of buffer queues, because it was mostly about pushing packets as fast as and as much as possible, and therefore routers got simpler. WDM had to get even more sophisticated, and that sophistication for WDM led to the adoption of coherent WDM, which happened to become possible exactly at the same time that DCI scaling started needed. So by now we have already wavelength division multiplexing using coherent that is capable of doing more than 20 terabits per second on a fiber, to do up to 800 gigabits per second per carrier, and achieve transatlantic, as you're going to see, connections at 700 gigabits per second per carrier. And on that last point, I thought to provide a data point on the current state of the art of the most spectrally efficient global fiber deployment, which you can pick different deployments because obviously spectral efficiency depends on how far you want to go. But this is, I think, an impressive example, because essentially Facebook wanted to connect Virginia Beach to Bilbao in Spain through a transatlantic fiber cable that they have a few fiber pairs, and it's called Maria. And in 2018, they deployed technology, coherent WDM technology that was developed for DCI initially, that was able to close that link of more than 6,600 kilometers with 16 QAM and more than 26 terabits per second in terms of capacity in single fiber, which translates for maximum spectral efficiency exceeding 6.2 bits per second per hertz. And here you can see all the details in terms of spectral efficiency at the different parts of the fiber C-band, red and blue. This operates at 16 gigavolts, and that is something to observe or note down for later. And doing 16 QAM allows us this type of capacity. Eventually, this was deployed at 24 terabits per second per fiber. which is, to my understanding, the highest spectral efficient fiber deployment today. And here it was reported in OFC 2019. And here you can see the spectral efficiency of Maria compared to previous high spectral efficiency deployments around the world. How was that possible? It was possible by combining coherent WDM and photonic integration. And DCI, as I mentioned before, was uniquely timed to get catalyzed by the coherent WDM that was coming up to maturity at the time DCI needed to scale so explosively. Obviously, at any optical coherent transmission presentation, let alone one at Stanford, I think it's fair to start with the work Joe Kahn did more than 30 years ago, introducing the phase shifting transmission systems using phase low semiconductor lasers. Eventually, it's interesting to point out that that work only became product for many different reasons, which we probably don't have time today to discuss. 20 years later, when the team at Nortel, now Sienna, productized this using the latest advancements in CMOS to build ASICs that will do the digital signal processing that will enable that technology to scale to the different IQ modulations, not just a simple phase shifting of 1 bit per symbol, but all the way to 16 QAM and so forth, and catalyze the type of performance that was needed for optical fiber communications and wavelength division multiplexing. There are many aspects that I can mention, and one should mention when discusses coherent into an audience, the improvement in signal-to-noise ratio, the improvement in the fact that the nonlinear effects get significantly mitigated by the fact you operate at constant power per carrier instead of the on-off keying and so forth. But to me, what is really interesting and not as often appreciated, especially by physics audience, much more so by electrical engineering audience, is the fact that coherent allows you to trade off very nicely capacity for distance, because you can have a carrier, a wavelength at 16 QAM, go with 800 gigabits per second for 800 kilometers today, or you can use the same wavelength with only QPSK and go 4,000 kilometers. And that trade-off between distance, essentially signal-to-noise ratio, and how much capacity you put on the wave, and then multiplex the waves to put total capacity in the fiber, was something that coherent allowed uniquely. And I remember in 2008, I was invited by Joe Kahn to give a presentation at the SPSC event at Stanford, and I was arguing of the value of such distance capacity technology, and soon enough, that technology came about and actually exceeded my expectations, and it was absolutely brilliant work by the Nortel team then, and eventually a few other teams in the industry to productize this. What was much less appreciated, and that's why I want to spend a couple of more minutes here, is the fact that wavelength division multiplexing would not have been able to adopt coherence so successfully if it weren't for the fact that photonic integration enabled the type of complex optical transmitters using the Mach Zehnder I and Q modulators shown here, and optical receivers on the modulation side to be implemented in a robust manufacturing way that allow volume and products in such a nice fashion if it weren't for photonic integration. There are many things one can say about photonic integration. This reference, I think, provides one of the best overviews of the topic. We simply state that by 2015, we have been able to scale from simple devices to devices that can photonically integrate in 3-5 materials. This paper specifically talks about indium phosphide, more than 200 functions. And the ability to build such photonic integrated circuits with hundreds of functions and then manufacture them in a way that does not compromise yield. The paper has a very nice reference outside the scope, the immediate scope of this presentation, that shows how that type of optical indium phosphide integration has yields that can compete with silicon electronics yields, because the number of critical defects over time reduces pretty much the same way like silicon electronics. Basically, your manufacturing process is as robust as silicon electronics. Proves how important that type of innovation is to allow today to build 1.2 terabit per second transmitters using such photonic integrated devices, and today integrating both receiver and transmitter on the same box, over the same substrate. So I don't think that I didn't think it makes sense today to go and summarize all the different innovations in coherent WDM and photonic integration that enabled the DCI to scale. But I thought this one example that I'm showing here is an excellent example of how coherent WDM and photonic integration coming together allowed the type of scaling that industry has achieved. And the specific example has to do with subcarriers. The idea of subcarriers is, instead of using the entire wavelength and send a single carrier down the fiber, to essentially send a few different smaller channels in terms of the frequency domain. Here, 8 are shown specifically. So instead of sending one signal with a 95, 96 gigavolts modulation on it of information, you actually send 8 narrow, if you wish, signals, the subcarriers, each one of only 12 gigavolts on it, that essentially constitute together the actual original channel. And the benefits from a physics and transmission down the fiber perspective are obvious, because you are dealing with an impulse response that is sufficiently more narrow to allow much better dispersion impairment and mitigation, reduce nonlinearities, achieve significant benefits in terms of optical signal to noise ratio. Subcarriers also, because exactly are building on a thing one on top of the other, can be very nicely parallelized and leverage in this sense the fact that digital signal processing was using these ASIC implementations, and which are inherently allowing for parallelism, to build all the digital signal processing techniques that they needed. And not only that, but then combine the two very nicely to play all the digital signal processing tricks that people in digital communications have developed, like water filling, pre-emphasis, and essentially optimize not anymore per wave, but per subcarrier, your optical information channel. Here in this specific example reported in this paper, you can see that subcarrier 5 on the edge achieves a spectral efficiency over the two polarizations of 10 bits per over these two polarizations, essentially something corresponding to something between 16 and 32 QAM. Here in the middle of the carrier, the subcarriers can go all the way up to 12 bits per two polarization symbol, essentially something very similar to 64 QAM. And on the other edge of the carrier, you only can transmit reliable information with 6 bits per two polarization symbols, more like something that will be essentially 16 QAM type of technology. And this gave a significant benefit, but the interesting question is how to build this. And that's where photonic integration came again to the rescue, because if you think about it, we're not dealing anymore with some channels that need to boot on the fiber, but a multiple of 8 in this specific implementation of the number of channels. Remember, the Maria had 45 channels multiplied by 8. That's a huge number. If you need to control each one of them individually, use the correct controls in terms of temperature, voltage, and everything else, where having these subcarriers implemented on a single substrate through photonic integration, in this case implement actually multiple channels, each one with 8 subcarriers over such single substrate, was an absolutely key enabling technology for making this a product, a reliable product. And here the graph at the very bottom shows the Q factor achieved for such an implementation. And because the specific paper assumes prior knowledge, I took the liberty to superimpose here a rather marketing slide, excuse me for that, which shows that basically with subcarriers we're able to gain 1 to 2 dB in Q value compared to what would have been able without subcarriers in such a coherent WDM system. And again, the point is combining DSP and photonic integration together, coherent DSP and photonic integration together, we're able to achieve a couple of dB better performance. Adding now on top of that all the tricks that digital systems, digital transmission systems, digital communications allow, most notably in the latest generation techniques like probabilistic constellation shaping, allowed us to come very close to the fiber channel limit. In this paper, the fiber nonlinear channel limit is shown by this figure here. So in addition to subcarriers, the superimposed techniques of digital signal processing like probabilistic constellation shaping, which allows about another dB or so of SNR gain. And you can see here we are just a couple of dB away from the channel limit. And that allowed us to take that same fiber.
Loukas, may I interrupt?
Yes.
I have a question. Would you be willing to comment on the number of photons per bit it now requires to achieve a good signal to noise ratio?
I believe that number, I don't have it on the top of my head. I'm pretty sure it's in that reference. And if it's not, I will take the action item to go back after the talk, find the right reference, send to you, May, so you can distribute it. I don't have it at the top of my head, how many photons per bit. That's a very interesting question. Yeah.
That question is by Ralph Page.
Okay, absolutely. And I'm pretty sure it's in the reference. The reference is actually the same here. But if it's not, I'll take the action item to find the number. Now, the photon per bit is also related, and I'll come to that, to the receiver sensitivity. So in some sense, it includes some other system details that are important to consider here. It's a multi-factorial answer. The point, if I may get back here, that the question raises, and it's an important one, is given how close we have come to the fiber channel limit, and just to build on the thing here, so take the same fiber between Virginia Beach and Bilbao that until 2018 were able to put 24 terabits per second in deployments with some margin, about a couple of dBs of margin, or 26.2 terabits per second at maximum zero margin error-free performance. With this type of technology today, and that's the really latest technology, this experiment, it's a field trial, not a research experiment, happened literally 6 weeks ago, and was reported for the first time only 2 weeks ago, and the research papers are not yet out. That's why I hope you don't mind I use this marketing reference here. The research papers will hopefully come out in the next couple of months. This latest technology allows now to put to 30 terabits per second over that fiber, which takes us to 6.5 bits per second per hertz in terms of spectral efficiency. So that's, if you wish, the absolutely latest and greatest state of the art in terms of spectral efficiency in DCI networks that will be deployed this year. So that is probably interesting from an industry perspective, and for those of you that want to know. What is even more interesting for me, and that's why I decided to spend the time to include it here, is if you compare the 2018 number, 24, to 2021 number, 28 terabits per second, or if you want to take the zero margin 26 to 31, it's exactly the same. It's a 17% improvement over a 3-year, one technology generation evolution. And that allows us, I think, some interesting insights that not many people that are not fully aware of the history here can appreciate. I have this slide here starting with 1997 because it describes where we were in terms of spectral efficiency when I was starting in the industry. The industry when I was starting was just adopting the 10 gigabit per second 16-channel wavelength WDM systems, which really meant a spectral efficiency of 0.0125 bits per second per hertz. And as we just discussed, we are already at 4 transatlantic deployments at something like 6 or 7 bits per second per hertz. And obviously in a continental deployment, US or Europe, we can go up to 10. So that's about 1,000 times improvement in 20 years, which, by the way, is 1.7x every 18 months, better than what the silicon speed could achieve at the beginning of the talk. And that was, to a great extent, thanks to the coherent WDM, which was the major innovation of the last 10 years and allowed us to get to the 10 bits per second per hertz, approaching so close to the fiber sound limit. However, exactly as we just discussed, the latest technology starts showing diminishing returns. And the graph I have here from Peter Wisner in the same paper that he reported the 1997 results, which I experienced myself when I joined the industry in 99, 2000. As you can see here, this is the research, spectral efficiency achievement, and this is the product. And you see both saturating and actually product catching up to research, because essentially we are at this interesting maturity point. So where do we go from here? Obviously, we can spend, and we will spend more effort trying to do better digital signal processing. Most of it, I'm told, has to do with better forward error corrections to mitigate, to build better digital filters, essentially to mitigate intra and inter-channel nonlinearities. But there is an interesting observation there that we're dealing with diminishing gains at not sufficiently supported power efficiency gains, because also CMOS is maturing. And here, for example, going from 5 nanometer CMOS to 7 nanometer CMOS, we expect only a 15 to 20% gain in terms of power efficiency, which means that if we don't gain as much from or in terms of the digital signal processing, it may not be very justifiable from a business perspective to build these massive chips to go do the digital signal processing. Then material science and optical physics has an interesting role to play. For example, extending the amplification band beyond the C band. L band is already happening. Additional bands are being discussed extensively. New fiber types are being discussed, including space division multiplexing. The observation I will make here is, I'm not an expert on this, it's very interesting work. The observation I'll make here is no major ecosystem or market adoption has yet happened on this type of technology. And I don't think that's unrelated to the fact that at the very beginning of my talk, that fiber construction is such an expensive proposition that people are very risk averse to adopt such new technologies easily. Doing some tricks at the network level with smart network analytics and system analytics to improve margin harvesting is another area. And this is nothing specific to DCI, but the DCI operators, the data center interconnect operators, the Googles, the Microsofts, the Facebooks, the Amazons of this world, because of the sophistication in software and the sophistication in machine learning techniques they have developed, they heavily look into this, trying to harvest the available margin, and there is more than 3 dB of margin. So imagine in the graph before, we are a couple of dBs away from the fiber channel limit, and we may spend hundreds of millions of dollars to build the next generation DSP to cut that by half, so gain 1 dB, where we are leaving 3 or 5 dBs on the table, trying to build networks with sufficient margin to be safe. It's an interesting proposition. And the last and most interesting for applied physics avenue of research that I see very active is to operate on higher gigavolts. So instead of 95, 100 gigavolts that we are today with the state of the art I showed, go to 130, 140, and 150. And this will not necessarily improve spectral efficiency, but that's fine as long as we keep it as good as the current one. But it will definitely, hopefully, improve power efficiency and cost. And cost is a different dimension I don't even include in my presentation, but happy to discuss it. I will spend only few seconds discussing the optical capacity gains by multi-harvesting. They can be of the order of 15, 20, sometimes up to 30%, depending on how you want to see it. Here I have some reference in terms of papers and further reading. The observation is some of the ideas are not new. We did with Alan Werner back in 2009 some interesting work using neural networks, back then was the name, machine learning today, to understand better the optical performance of the fiber and improve optical performance monitoring and proactively analyze what will happen in the network. That's the basic idea here. We just have much better tools and substantially more motivation today. The other reason I decided to include this 1 minute on this slide is because the same techniques of machine learning, network analytics are being explored to do some very, very interesting works in terms of environmental analytics and testing and sensing. So Google, for example, has reported a couple of papers the last 12 months using their global fiber infrastructure to measure earthquakes around the world, including subsea earthquakes in the Pacific and Atlantic. So some very, very interesting research, I think, there. What I want to focus a bit more in is the physical challenges operating at 130 or 150 gigabits per second. And I will organize them into the material frequency response aspects. For example, John Doe, who spent a distinguished career at Bell Labs and then joined the silicon photonics company Acacia, that will become part of Cisco this year, reported at last OFC that he thinks the silicon photonics frequency response may be limited after 90 gigahertz, which means up anything more than 140 gigabaud operations, because the way he calculated the depletion region in silicon, he assumed 200 nanometers and assuming a specific electric field of the order of 10 to the 4 volts per centimeter, he thought his carrier velocity will limit his frequency response to anything more than 90 gigahertz. I don't know that I agree 100% with his work. I think silicon photonics people can play some interesting traits, but because he's a silicon photonics expert, I wouldn't second guess him. The other aspect has to do with digital analog converters and the DSP, and there is work in progress, more on that a bit later. And the third and really interesting aspect is the electrical interconnects, because if you ask people in the industry, they will tell you that the connections between the DAC of the DSP and the driver today is one of the main limiting factors. And that's why people start discussing interposers and flip-tip drivers and versus wire bonding and the SRR, the signal to noise limitations on the PCB and the connectors and so forth. And the observation I would make there is obviously all this comes mostly from thermal noise. So people use super advanced cooling to minimize that noise and what have you. Some very, very interesting physics challenges. In the remaining 5 minutes, instead of getting into more details, I'm not an expert anyway on some of that, I thought to change a little bit gears. But before I proceed, let me ask May, is there any other question, any other comment? Is that, Bert, is that going sufficiently in speed, or am I going too fast, too slow?
You're good. There aren't any more questions so far.
Thank you. So in the remaining 10 minutes, which I think I have, I want to change gears. And this would have worked well in the live audience asking that question, but here I will spare the interaction. Basically, on August 3rd, 2006, Amazon announced AWS, the Amazon Web Services, with the first service, the Elastic Compute Cloud. And that may sound not very important for applied physics seminar. It's definitely important for the networking overall, because cloud has been a very important transition, but it is because the massive explosion of cloud, and this is one of many references that show how much compute shifted from traditional data centers in the green to the cloud in the red, motivated a brand new type of metro DCI network evolution and some really interesting associated photonics technology evolution. Specifically, the fact that cloud has become so pervasive motivated all these cloud operators to build these availability zones in each region they operate. And these are essentially metro DCI networks that need to be less than 100 kilometers of fiber path. And that comes from the fact that they have multiple data centers, and for network availability and service availability reasons, they want to replicate everything that happens synchronously in all these data centers. And in order to achieve that, the available latency budget they have ends up being less than 100 microseconds. And if you deduct all the latency that comes from switching, ASICs in the switching networking chips inside the data center and so forth, that essentially tells them don't go more than 100 kilometers of fiber between these data centers because the speed of light will introduce more latency than you want. And that was essentially what gave rise to the metro DCI network evolution. And that was substantial. In the already exponentially growing DCI networks, now we have a step function because people start deploying these metro DCIs massively. You see a factor of 5 or 6, and the adoption has been really big. And it coincided with the adoption of the 400 gigabit Ethernet technology. So people start wondering, I have all these technologies that I developed either for technologies very close to data centers, inside or campus, and for traditional long-haul networks. How do I go and address the new need that has come about? And the answer was to develop a metro-optimized 400 gigabit Ethernet coherent WDM pluggable technology. And the pluggable comes from the fact that I want to leverage the volume, the economies of scale and the volume manufacturing that existed in these optical pluggables inside the data center. And in order to do that, again, I had to use photonic integration and DSP, coherent DSPs, but this time improved by 500%. And here it shows how the challenge fitting everything into a pluggable, which is no bigger than the size basically of half an iPhone 6. And you had now to put all this technology that before was put on a 5 by 7 inches module inside a module that was 1 by 2 inches or something like that. And that, again, brought the value. And given the success, because indeed there are products today, as you can see, it is predicted starting this year to become massive. We're talking about hundreds of thousands of ports. And that is not only because it's going to address the 400 gigabits per second, 400 gigabit Ethernet, but also scale to 800 gigabits and so forth. There are already proposals out there. Some people actually go a step further and say, let's use it for long haul and change the way we build networks by regenerating more often. This is a cheaper, more power efficient technology. That is a separate talk but in its own right and still unclear. There's a lot of debate in the industry. What is very clear in the industry is that given that coherent interconnects have been achieving significant power and density benefits and cost benefits according to the projections on the cost side, this type of DCI coherent interconnects are going beyond the metro to start getting into the access and campus, essentially exploring different use cases in this space bandwidth product type of evolution. And this is something interesting to watch. Obviously, it has to be connected to technology, product transitions in the industry that relate to technologies. For example, in the access 100 gigabit Ethernet, in the case of DCI, 800 gigabit Ethernet, and so forth. Here I report some very recent results just 2 months ago at ECOC on 800 gigabit Ethernet campus DCI, where coherent DCI technologies are trying to replace intensity modulated direct detection technologies. And here you see essentially the limitations of intensity modulated direct detection technologies mostly by chromatic dispersion, and that's where these coherent products, many believe, can make a difference for distances more than 3 or 5 kilometers. Obviously, that depends also on when exactly the adoption of this 800 gig will happen, and there is some interesting debate whether it's 2-3 years from now or more, because that will tie also with what kind of technology, coherent technology, will be mature enough to use in this type of product. Again, some of the system trade-offs.
I have a question, Loukas.
Yes, please.
So someone had a question, and the question is, there are so many photonics startups. Are there any companies that you see as disruptive or interesting?
I won't comment on companies because I work for one. It's not a startup, but I'll be happy to debate that with the person that asked the questions over email. I don't think on a public forum it makes sense for me to make any comment. There are many interesting startups and many interesting non-startup companies. The only thing I would say, which I was planning to say at the end, but since we're coming close, I will say now, is that photonics is experiencing a resurgence. When I graduated from Stanford in 2000, Cisco has spent about $4 billion acquiring photonics optical companies. Cisco spent this year again $4 billion acquiring Acacia. So I leave it at that. Definitely living a resurgence. What I do want to say is that in addition to DCI, subcarrier technology that I discussed before has some very, very interesting applications on the axis, because it's the first technology, to my knowledge, that essentially productizes optical frequency division multiplexing to enable point to multi-point technologies. Don't have time to get into that here. There is a reference or actual demonstrations already happening. So I'll proceed because I do want to touch on this, which I'm sure is in the mind of many people, and that is how far can DCI technology and coherent and photonic integration would it get inside the data centers? And obviously, inside the data centers, we're dealing with an optimization problem that includes many different technologies, compute, storage, and so forth. But the key observation is that optics, networking overall, and optics specifically start eating more and more of the power budget that is available in this type of technologies. You can see here overall how the power budget is being distributed today and in the future. Networking starts getting, it's the only one that is growing more, and here per specific technology. And I think that's evidence of the increasing importance of that optics have to play. There is a lot of debate on how to solve that. There are some proposals out there to bring closer essentially the optics to the ASICs to minimize essentially the electric line charging dissipation. But I don't think we have time to cover this today. I just think it's a very, very interesting discussion because in addition to some interesting physics, there are some very interesting problems in terms of connectors and manufacturing and so forth that are brought. There is some interesting trade-off. The only reason I brought it up here is because essentially that goes a bit on a different direction than the pluggables, more in the direction of photonics integration. I will summarize by reminding you that given the massive growth of DCI, a massive dedicated global infrastructure was built that was able, thanks to technologies that were developed essentially by research that happens at Kingston and other applied physics departments, in terms of coherent WDM and electrical engineering departments that essentially matured coherent WDM and photonic integration that allowed us 1,000x term of spectral efficiency gains over the last 20 years. And the remaining challenge ahead of us is also very interesting because the cloud is growing for sure. And I will leave you with that thought because I thought that much like when 20 years ago I was motivated by similar joke by Gilbert in terms of an architectural revolution, I think now the power efficiency challenge motivates some very interesting work that has to do with Kingston and Applied Physics. Thank you. Hopefully it was useful.
Yeah, thank you very much, Loukas, for an enormous amount of information. But I think the message is very clear. This brings back kind of the excitement there was in the electronics time, several decades ago. You see these enormous growth rates, and that is now kind of leveled out. Though optics is, the kid that is growing up on the block and is having a huge impact. So thank you so much. I don't know if there are any more questions. We're almost out of time here. It's 1 o'clock. If you do, please ask them now. Otherwise, I would like to thank Loukas for his presentation, and wonderful to see this overview of the kind of things that happened between the time that you left Stanford and 2021. So thank you so much.
Thank you too. I hopefully it was interesting. I definitely enjoyed it.
Yes.
And I look forward, by the way, answering any questions that people want to ask offline. Just send me an email. I have my email here, and May has my email. So I'll welcome all your comments and questions, especially the most critical ones. Don't be shy.
Okay. All right, we'll do that. Thank you very much, Loukas. So we'll
thank you.
Yeah. Okay. Bye-bye.